the stand?
Yeah, I must have left it at home. Oh, all right. All right, guys. Let me first give you guys the answer key for that practice test I gave out last time. Next week, I'm going to wheelbarrow in all of your past homework assignments and give them to you with, just like I did last time with the answers from the sections, the most recent sections. I'll give you just the answers from all of the sections, so you can go back. Anything I didn't have time to actually look through, you can go back and double check your answers. Oh, that's it? Okay. Really jipped this road.
No, I miss. I'll take stickers.
You still need?
Nowadays.
Is everybody all right? Everybody got a copy of the answer key? Today we have somehow a lot to do, so I want to. There's a couple ideas from 14.2 that I want to cover. 14.3, thankfully, is relatively easy. I always have to preface that with that word relatively. Not necessarily easy, it's just easier than the previous section, I think. We'll see if you guys agree. There's actually an idea in 14.3 that's exactly something from differential equations that you have to be able to do that we can do here at this level too. Has anybody taken DiffQ yet? A few of you guys. So exact, you guys remember exact differential equations, roughly? And there's a test to see if it was exact. So this will be very familiar when we do that today. Yeah.
Before we start off on 14.2, is that okay?
Do what?
On 14.2.
Yeah.
The concept that you said with the integrating with like perpendicular, like where the vectors go out and then there's the vectors that go around and the circle and which one is easier than?
So remember, the only vector field integral that we've looked at so far deals with the tangential component, right? So if I have a curve that it's, the way the curve is drawn lines up with the way the force, the vector field is. I keep wanting to say force field. The way the vector field is, then that should be kind of like close to a maximal output, right? So the idea is this. If I have some force field, oh, that's beautiful. If I have a vector field, and the one we did is really the easiest visual there is, and this kind of goes like this all the way around, right? To maximize the interval we've looked at so far, meaning the tangential one, I would not want like a straight line, right? That would actually have the minimal, it would be 0. How much of a straight line would lie in the direction of these arrows? None of it. It would be perpendicular to those arrows, right? So for the line interval we've looked at this point, which is the tangential piece, the way to make it maximize it is to have a shape, in this case a circle, that kind of mimics the shape of the field itself. Cool? Now, I mean, you could do other things. I mean, if I had a line like this in this field here, and actually there's a question like this on the test, on the practice test. Do you think that that would be maximized or minimized? Would that be positive or negative or 0? What do you think? Along this curve, does it match up with the components well, or does it not? Does it go against the curve or against the field or with the field? for the most part. It goes with the field for the most part. So the integral of this, the tangential piece, would be positive, right? Of course, how would I make it negative? I would just point my arrow down. Then it would be overall against it. So it's the idea of if the wind's blowing this way and I've got to go over there, I'm going to kind of like do this thing. So I'm going against the wind. Or if, in this case, the wind is blowing this way, so overall I'm kind of going with the wind. A little bit against it here and a little bit not really against it. It's just not perfectly lining up with me, right? Here it's perfectly lining up with me. It's right in my back. Here, it's blowing this way a bit, but it's still got a component going in the direction my field, my curve is going. So the tangential integral here would be positive. Yes?
What about for the 0 one? Like, what would it look like?
The easiest 0 one for this would be like any line, any radial line coming out. Any line coming straight out through like this, because it would be perpendicular to all my arrows. Right? So that's the simplest one.
Oh, okay.
Anything else where they all the pieces cancel out. So for example, let's see what's a good easy one. So if I have something like, let's see if I want to deal with this here. I need a different field to work with. So if I have, let me draw a few more for myself here so I can make this look a little better. Okay, there. So if I had something where they cancel out, like if I have a little line like this, that's going to be positive. That's great. If my line goes maybe something like, let's see. What would be a good idea here? If I went something like, Jeff just put something down. Something like this here. This is kind of weird. Well, that's not the perfect thing. But this is not going to be 0, but do you see how this piece is going along with it? But this piece would be going against it, right? For the most part. So they don't cancel perfectly, but this at least gives you an idea. If at some points I'm going with it, and at some points I'm going against it, those would cancel out. If I'm going perfectly with it and against it, like they balance out.
So if you have like two lines on the graph, then basically.
Yeah, if I had
going with it, and then on another part you're going against,
cool.
then okay.
Cool. Not the easiest thing to come up with on the spot, but yeah, you have to have some kind of field so that you can have a field defined almost any way you want to. So I can have a field like this, and then I can say, well, I'll have my line go like this maybe. Then part of it is whatever part here is going to be canceled out by the part here. That's not still not perfect, but if you have sometimes it's blowing against you, sometimes it's blowing with you, then they'll cancel out and become 0.
Okay.
Another way to get 0 is you just never ever go along with it. You're always perpendicular to it. So that's why I said the easiest one here to get 0 would be this. Anything radial, because then it's always perpendicular to the vector field. Cool. Okay. Now some of you guys might realize I did say that we would have 2 different types of integrals. One that was tangential, the other one must be the one that's normal, that's orthogonal, right? That would pick up then. This would be the maximizing for that type of integral. We haven't quite looked at it yet. Okay, cool. All right. Any other specific questions about, or general questions about? Okay. So, I think last time we left off, we did a couple of examples, and I want to get to a point where I can show you a different way to do a couple of integrals. There were several different ways to write the same integral. If you'll look back in your notes, you've got this here. Of course, until we do some of this stuff, it doesn't really mean much of anything to you, so that I understand. So this is the integral we've looked at so far with vector fields. That's the tangential piece of the vector. So this is what we looked at so far. And one way to write this was here, understanding that f FGH. So it's defined to be some kind of function component-wise of a vector. So each component of the vector is some function of x and y, or x, y, and z, depending on how many dimensions you live in. So this would be, assuming it's FGH, this would be fx prime plus gy prime plus hg prime, which is also the same thing as so each of these three are the same thing. And this way is the way that we normally do it. And actually, we write this a little bit differently sometimes. We write this as f dot dr. But this is the way we did a couple of problems like last time, where we said all we have to do is find the how to write C parametrically. That defines what x, y, and z are, or what x and y are, depending on how many dimensions I'm living in. And I rewrite f using that definition. And then it's just a dot product between the two things, right? So maybe we should start with doing one more example like that, and then we're going to try to finish up stuff, and then we'll desperately try to fit in some review. All right. So one example we could do. Interesting. Here we go. Perfect. Well, let's see. I want to do something. That's not the most interesting thing. 35 maybe. On page 985. And I'll tell you this, the practice test, I really did make it this time a little harder than I intend the actual test to be, just in case you started looking at it and you're freaking out a little bit. Your homework, for the most part, doesn't have a lot of contours defined by several separate line segments, right? You don't have a lot of triangle regions in your homework. But on the practice test, I said, what the hell? I'll just give you an ugly one so you can see how it works. You just take each piece of it one at a time. It's like several single segment problems, and you put them all together. Not a huge deal. So let's try one that's a little more direct. This one says my vector field is this. And I want to do it on a line segment 1, 1 to 5, 10. So this is my C. This is not the one we did last time, is it? No. No, I can't remember what one it was. So they have to tell me, they really have to tell me what interval they want me to do, since there are a couple different options. And they do tell me they want this one here. Yeah, they tell you right up there. What's the first thing I want to do here? What are my steps to go through? And if you remember that one handout I gave, it actually has those couple steps up there in the very first thing.
Subtract those points first.
Good. So in general, the first thing to do is to take your C, and if it isn't already, write it in terms of R of T. Turn it into a vector equation. So in order to do that for the straight line, I do 5, 10 minus 1, 1. And that gives me 4, 9. And what is that really? It's the direction. It's a lot like a slope. It's exactly the slope, right? And so to get my equation of the line, then what would that look like? Good. 1, 1 plus C times 4, 9. And just to make this a little more compact, we go ahead and put this stuff together. I get 4t plus 1 and 9t plus 1. Now always double check. Whenever you do this for a line segment, you're going to be guaranteed that t goes from what to what, to pick up both between both points. The way that we worked it, we forced t to go from what to what? 0 to 1, right? We forced that because when we do the subtraction and use this as a slope, we're saying one step takes me from this point to that point. And t is the number of steps I take. So we force t to go from 0 to 1. Which is always kind of nice to do. Doesn't really matter. Alright. Now, what do I want to do? Now I've got this thing written parametrically. What do I do next?
So we always force t to go from that range?
No, I want to be really clear about this. It could go, I don't care. And in fact, I think we said last time that if I made this, if I made this here like twice as much, then t would have to be at most 1/2, right? I mean, it kind of depends on what they give you, what's easier to work with. It's not always going to be a straight up line segment, so sometimes it'll have to be 0 to 2 pi if it's circular, or 0 to pi if it's half a circle. But whenever you have a line segment, if you do it this way, t is going to be from 0 to 1. 0 is the starting point, and 1 will get you to the ending point. It doesn't have to do this. It doesn't have to. Cool. So now that I've kind of defined, and what does this really do for me here? I was about to just say it, but what does this do for me? What is this piece of it? The x piece. So now I know x is this. In order to be on this line, what's got to be true about x? X must be written as 4t plus 1. And y must be written as 9t plus 1. Or must be able to be written that way. So then I take my force field, my vector field. I just want to say that. And I write it in terms of those. So what will that be? 9t plus 1. 4t plus 1. Now, in order to do this, if you remember this, to do this, it's really f r prime, so f with the t's in it, r prime dt, right? So what do you want to do next? Find r prime. And now it's kind of like that speed. It takes into account how quickly you're moving along this curve, which we don't have to worry about in just dy dx terms, because dx is going to be by 1 all the time. In this case, my curve is going crazy, and I have a lot of different ways how quickly I want to go through it. I've got to take that into account somewhere in the interval. How quickly I move along this line for every step I take. So what is r prime? And of course, in this case, it's like, well, of course it's 4,9, because that's the slope, right? So 4,9. So what's the magnitude of r prime? Yeah, square root of 97, cool. So to put my whole integral together, what I can do on the side here is do f, what did I leave out here? Oh wait, no, this is dt. F dot r, oh now I'm forgetting now.
That was like FTDS and FSTS.
Oops. Oh, okay. Oh, no idea. Oh, that's one. I'm mixing it up with the stuff from before. Silly. Yeah, okay. Alright. So I should go with what I've got written down here. So it's this here, right? So for what I was doing is I was getting mixed up with the line integrals of scalars. So when you do line integrals over scalar functions, that's where you do the magnitude of r prime. And that's because you have the integral of f ds. That's when you're dealing with functions that are scalar functions, meaning that the outputs will be just numbers. When you have functions that are force field or vector fields, so the outputs are vectors, you need to do this dot product between f and r prime. So here's my r prime, right there. So now I need to do the integral of f dot r prime, which is really what that says. So what's f, one thing you can do on the side here then is what's f dot r prime, you can get that done before you go to put this into the integral. So what am I going to integrate? What is f dot r prime? So here's my f, there's my r prime. Dotted with 4, 9. And what do you get there? The dot product, of course, is going to come out with, is going to be a vector, or what's going to come out of a dot product?
It's going to be scalar.
Just an expression, yeah. A scalar once I know what t is.
Yeah.
So in this case, I'll get 36t plus 4 plus 36t plus 9. 72t plus 13, yes.
Since your f is in yx, shouldn't your point also be yx as well, since you're dotting it? So it should be 9, 4. Or
Now r prime is 4, 9, period. Now why did this guy, and that's, you actually can bring up a really good point. It's really easy to mix up. This function can be written any way it wants to be. What sets up what x and y are parametrically is right here. Right, so I set up what x is and I set up what y is. So the function can put them wherever the hell it wants to. This one's kind of simple, all it does is it turns them around. Cool, so this guy has still got to be in the right order. Right? So I get this, now this is the function that I want to integrate. And what do we say t goes from to? 0 to 1. This is the way we set this up. So anytime you have a line segment, you can actually make it so that it's 0 to 1. You don't have to, but it almost always will be. Okay, cool. So what threw me off is I think I wrote this up here in terms of the old scalar approach, which is where you involve this guy. When you have vector fields, that's when you want to dot product at that with the tr. Here there's no vectors involved, so it's just a straight up multiplication of with the magnitude. Here I want the dot product. Then it kind of inherently has the magnitude in it, right? So they do still end up being the same thing. So what do you guys get here? And of course then 0 is going to be nothing, and when you plug a 1 in, 49. Cool. Now, I said this last time, it's really easy to lose what you just did when there's no physical meaning behind what they give us. There's no they didn't give me any physical meaning behind this. Or behind that even, it's just a line segment, who cares? So it's really easy to lose what we've done. But to me, the nice thing I always try to keep in mind is for vector fields, when you do this integral, you are just kind of adding up how much of that vector field actually lies in the same direction as your curve. Right? So that's why a million years ago when I took this, we had to draw the vector field for every problem so that we could kind of make sure that at the end it made sense. So if my vector field was like this, and my line segment was like this, I would expect my answer to come out positive, because overall it lies pretty much in the same direction, right? Whereas if it was like that, I expect it to come out negative. So I know that it at least makes some kind of sense at the end. So this comes out positive, which means if I drew this vector field, that curve would overall be lined up with that, with these vectors.
what curve?
This curve.
Oh, line.
Yeah. Sorry. In math, we call everything a curve, even if it's straight. That's then a straight curve. Yeah.
One other thing that kind of confused me is sometimes you write a vector field as yx, and sometimes you write it as negative yx.
Okay. This is a function. It could be anything you want it
so
to
if
be.
they give it to you.
In this case, the inputs are two-dimensional. just x, y, they're just points, right? So I could have a vector field defined over 3 inputs, right? So in this case, they just decided it to be this. It could be anything. It could be natural log of x, y, comma, sine of the square root of x. Thankfully it isn't. Right? The integral would suck. But it could be anything. It's just, this is just a function. It happens to be a function whose outputs are what? What are the outputs for this function? So what is f of 1, 3? And what is that thing you just said? It's a vector. So at the point 1, 3, at the point 1, 3, if I wanted to try to start drawing this thing, at the point 1, 3, I have a vector that's pointing in the direction 3, 1. So it'd be pointing in the direction 3, 1. So it'd be pointing like this. Do you guys see that? A little bit? So that's what we were doing before, was just drawing vector fields. You have definitely not done enough drawing of vector fields, and I think not many people have, that you can just look at this and go, oh yeah, it looks like this. Like we can do with just everyday functions. We can look at x cubed plus 2x squared and kind of know what the hell it looks like. I don't really have a feel for what the hell that looks like. I have to draw a few representative points. Right? But that's kind of looking good for 1, 1 to 510. 1, 1 to 510 would be this. That would be my curve, right? So my vector field, at least this piece of my vector field, is kind of agreeing with my curve. And if you do a few more representative points, 2, 1 would be 1, 2. So right here would point in the direction 1, 2. So now you can kind of see why the answer came out positive and actually a decent distance away from 0. Because it is lining up with the vector field.
Yeah, that makes a lot more sense.
Sweet. That's my favorite phrase in the world. All right. So it's kind of so what I'm gonna probably do on the test, since I have to have you do a drawing of a vector field anyway, I might ask you to draw a couple that will then have integral problems to do with them later. Sort of like on the practice test, there's that one problem, number 4. So I could do one like that, where you have to kind of predict what it would be, and then I could follow it up with an actual problem that relates these things, and then you have to see if it actually comes out the way you thought it would.
Get a copy of the.
Yes. So real quick, while we're looking at this thing, 4a, how do you think that would come out? Would that be positive, negative, or 0? Positive, because overall it's pointing basically in the same direction as the vector field, right? Your curve is in the same direction as your vector field. What about part B? Yeah, because for the most part it's pointing against your vector field. Yeah. So it's that simple. So if I followed it up with a couple questions that had this vector field function given to you, and then the curves that give you what point it goes from to, you'd know what to expect from your integral. For the C2 one, you better get a negative number. For the C1, you better get a positive number. And then you at least feel good about that piece of it. What the number should be itself, that's a little harder to get a hold of. Okay. So quick little I want to point something out. Where'd it go? Here we go. Yeah. Oh, okay, well. It's too bad. Yeah, so what's kind of interesting on this little handout I gave you, they have line integrals for scalar functions. And that's where the v of t comes in. That's really r prime of t, right, the magnitude. So right up here is the little thing for line integrals of scalar functions. The work, the funny thing about the work is it's basically the same as just a line integral of a vector field. So if you look up here, this one talks more about what we just did, integrating over a vector field. So that kind of gives you the different ways to represent that. The last couple things out of section 14.2. The first one is actually something we've already done. It's just a definition. So the one thing that's different here, we've already basically done this. This involves the integral over curve like that. So this is the integral that we're used to. The thing the book doesn't do yet, it actually references the fact that the next section they'll do it, and I'll just go ahead and do it right now. If I have a closed curve, and what do you think that means? Would this be a closed curve?
No.
No, because it doesn't come back to itself, right? So a lot of the things we talk about in physics and engineering involves closed curves. I kind of complete the loop. So when I have a closed curve, to represent that in my symbol, I just do this, which is kind of nice, right? You probably actually want to close it. To make it clear that I'm working with a closed curve. Some functions will have very easy integrals on closed curves. What do you think some functions' integral should be if the curve is closed? Some functions should come out to be 0, right? And those are the kind of functions I was talking about last time. The functions that are created by taking the derivative of something else. Those integrals should be easy. I should be able to apply the fundamental theorem of calculus. What the hell was that? That was this guy. The integral of f from a to b is fb minus f. Hey, remember big F was the antiderivative? Remember that a million years ago? That's the fundamental theorem of calculus written very quickly. So if I have basically A to A, because that would be a closed curve, right? There are only certain vector fields that act like this, though. You have to realize there's a lot more that could go on now with these things. Some vector fields, you have a closed loop, I don't care. It's still going to be, in fact, we saw one already. This one would not do that. Here's a closed curve. Would this integral be 0? Over that closed curve, would it be 0?
No.
Careful. No. It would actually be the biggest it could be, right?
Yeah.
So we have to kind of, the next thing we're going to do is we're going to investigate what kind of vector fields actually allow me to use the fundamental theorem of calculus, because then their integrals are easy over closed curves. They're 0. If you come back to where you started, sometimes it should come out to be 0. That kind of makes sense. But not all of them will do that. And there's a very simple example. If I just said it, it would make no sense. Why shouldn't they all be freaking 0 if you just come right back to where you started? Well, here's one reason why. Right there.
So if the vectors are pointing out all the way around, it would be 0, right?
True.
Okay.
But that's more just because the curve you drew is always orthogonal to your
Okay, what if they're all pointing in one direction? It would be 0 because they would all cancel each other out.
There's an idea. Cool. So if they're all pointing like this, and you draw then you draw a circle.
Circle.
Yeah. So that might represent what's called a conservative vector field, one that works like that.
Because the ones opposite of each other would cancel each other out or something like that.
Because here you're going against it as exactly the same amount you're going with it here. And then these points you're orthogonal to it. So all the pieces that are lining up cancel with all the pieces that are not lining up, that are exactly opposite lining up. That's what we were trying to say earlier. Cool. I like it. All right, so circulation is really just this. So the only new thing when they talk about circulation is that your loop, your curve is going to have to somehow be closed. It doesn't be circular. It'll be some weird ass thing as long as it comes back to where it started. Then when I do that integral, it's officially called the circulation. So that by itself is nothing new. It's just dealing with that integral over a closed loop. The thing that's new is the flux. And normally the first thing that comes to mind for me is Back to the Future, flux capacitor. But another thing that's more useful really is like a magnetic field. You guys know that if you take a closed loop of wire and you move it through a magnetic field, you cause a current along that wire. So the flux is defined to be the field lines of the magnet the magnetic field lines actually pass through that loop. So it's more like an idea of passing through something. Whereas this integral up here was lining up with something. This one seems to be the one then that's the other part that I've been promising for a while, the part that's orthogonal, right? So instead of doing an integral of f dot t, we must do an integral of f dot n, where n is, of course, the what? Normal vector, right? Because that would signify then something that's orthogonal to that. So if I do f dot t, I'm in the same direction as my curve. F dot n, I'm in the opposite direction. Just to cut to the chase, and I will highly recommend that you read through, it's in here somewhere, here we go, page 983. Because figuring out what this is, it's not difficult, it just takes a little bit. Thankfully not for each problem. You do it once, and then you set up the interval, and then that's what you always do. So let's see if this makes sense. This integral actually comes out to be in this case, I think they're in 2 dimensions for this one here. F is
What problem is it?
Fg. This is just the definition.
Oh, okay.
Oh, and how did they define? Oh, okay. Let me put this up here too. C is okay. What this comes out to be, and let's see if this makes sense. This comes out to be Fy prime minus Gx prime. So it's kind of like that cross product idea, right? And whenever I think of cross product in 2 dimensions, it makes total sense. The dot product goes straight. The cross product goes crosswise. F times y and g times x. So if you remember your little, if I put f and g and x prime, y prime, what's the determinant going to be? Fy prime minus gx prime. Cool. You guys get that? So if I have a vector field over 3 dimensions, x, y, and z, I'll need the larger determinant to work with, right? And that, I'm not going to do too much with that, but that's on page, actually it's not in here yet. They didn't do it, yay. So all we have to worry about with flux is 2 dimensions, thank God. 3-dimensional one is a little bit more to work with. So the easiest example of this is really exactly the same as the easiest example with the tangential. A field like this, what did that not work well with tangential integrals would be a circle, right? But what's this going to work beautifully with as far as normal, as far as orthogonal? A circle. So now, where, as before, the interval that was tangent, the tangent pieces, it wanted to line up with the vector field. Now to make the integral, this integral maximum, I want to be orthogonal to that. So to make this maximum, I'd actually want my curve to be a circle. So if I have radial, something coming out like this, so this is C1 or C2, that's going to be 0. Because none of it is orthogonal to the vector field. But if I have a circular curve, all of it is orthogonal to the vector field. So that's going to be a maximum integral then. Okay. So let's actually do an example. See how this thing works. A little more interesting than that. So now to do this, it's kind of similar to what we did before. But there's a couple different ways to come at this. And there's actually one other way to write this here. You can write it like that. Sort of similar to what we could write the tangential interval. There are several ways to write that. So in this case, I've got this here. What's the normal to this going to be? I don't know if you guys remember. So basically this is xy. What's the normal to this going to be?
Negative sign.
Yeah, negative yx, so negative sine cosine t. Oops. Cool. So one way to kind of do this is to actually just take it the way it is there up here. Just do f dot n. So what's this written in terms of, now that I've set this up, this was given to me, this tells me what x and y are. So of course this is just going to be the same thing. So my f now could be written as cosine t sine t. What's my f dot n going to be then? Plus, yeah, in this case it's going to be 0, right? Negative sine is going to come out to be 0. Cool. And if I want to do of course I mean so. Oh. Okay. So if I want to do it this way, it's actually the way we really need to do it. Let me see. Actually, I wanted to do one like this anyway. So the way they gave this to me was xy. So f is x, g is y. Coming from here, f is x, g is y. R was this, cosine t, sine t. So f is cosine t. Y is sine t. So what's y prime? Cosine t. And what's x prime? Sine t. Cool. So putting this back together, what do we get?
X prime is negative sign.
Yeah, where'd it go? X prime, x is cosine, yeah, good. So f times y prime, f is cosine, y prime is cosine. G is, oops, G is sine. And x prime is negative sine. And to get all the way around this circle, I of course want to go from 0 to 2 pi. And then you get 1. It's awesome. Integral of 0 to 2 pi is 1 dt of 1 dt. You get 2 pi, which makes more sense because if, like we just said, if it's normal, from doing the normal part of the vector field, then a circular curve should have the highest integral possible, right? Because now it's going to be orthogonal at every point. So this should not come out to be 0, it should come out to be 2 pi. over here, I was making it a little, I was trying to actually cut some corners, and I shouldn't have tried that. I was trying to get directly to what this is, but that N is not the easiest thing to find directly. So really, the easier way to go about it is this guy here, for the flux. And there's not too many flux problems, because like I just said, the normal curve very often is very difficult to find. So that's why they really didn't give you very many flux problems in your homework. They really just gave you some more visual problems so you can answer some questions about the flux for a given vector field. So what I really want to do is come back to some problems we've done before and show you how this formulation here, because we haven't done an integral like this until just now. I mean, I've written this format up here for some of the other integrals we've done, but we haven't attacked one like this yet until just now. Yes, ma'am?
So you want f dot n equals 0?
I didn't want that to equal 0. That's why it was over here, and that's just because I got the n the wrong way. So that was my mistake. On this kind of problem, it's a lot easier to do it with this form. That's a lot more direct. The f and g come from your force, your vector field. This x and y comes from your parameterization of your curve.
You take the derivative.
And then it's just derivatives and you plug it in and go to town.
How do you know which one to use?
This one I'd use if I could find the normal vector easily. This one I use actually most often because this one's the easiest to put together. They have to give me f and g directly. They have to just give me those. And these are just derivatives of my parametric equations, which they also have to give me somehow.
So the normal vector should have been cosine comma negative sign?
Yes, cool. All right. Let me see. All right. So on the test, I'll obviously kind of do sort of like what the homework is that I've assigned. So there weren't really a lot of flux problems directly. And I'm going to put down on the test the different formulations of the integral, the tangential integral. So remember there are 3 different ways to write that. So one thing I want to come back and do, and actually we're going to do it in this next section, is show you what the integral looks like in some of those other formulations. Right? Because sometimes it's easier than rather than going through the whole R prime business, just to do it more directly. This next section is kind of nice because the math is really straightforward, believe it or not. And the idea, hopefully it kind of made sense what I was saying at the end of class last time. If I do have a vector field that was created by taking a derivative, its integral should be that much easier to calculate that, because then I'm just undoing the derivative. That's exactly what we do. There's got to be a test, though. I can't just look at a function and tell, oh yeah, that came from a derivative of some other function, because this involves partials. It's not quite as easy to tell just by looking at it. So one skill we have to develop is how to integrate directly what's been partially differentiated. And that sounds difficult, but it's actually really nice. It's kind of like a puzzle that, personally, I really like this stuff. And it's from DiffyQ, which is very meaty. You can do a lot of stuff that's not too vague. So here's the idea. A conservative vector field. And there's a couple things I kind of have to, I really don't have to do this actually, to tell you honestly. But if you look on page 988, just to make sure you understand if they say these things, what they mean by this. We already know what a closed curve is. It comes back to itself. And it's not allowed to really cross itself. That would be not a simple curve. So this is a closed curve. And it's simple. And of course this is not closed, simple. So what's it mean to not be simple? It means something like this. This would be a closed, non-simple curve, and then it kind of runs across itself, right? And how would you make a not closed, not simple, where you just don't close anything and you have it run like a little fish, right? So these are both, this is closed, not simple. This is not closed, not simple. All right, that's really as much as I want to say about that. For the most part, it's sort of like every now and again they'll tell you that there are some functions that this kind of thing won't work for. We rarely, if ever, see those functions until you get to some higher mathematics. Then you really have to figure out ways to work around that problem spot. Here, they want to make sure that you understand what these words mean, because they're going to tell you stuff like, well, we're working with a closed simple curve. Then you know that certain theorems work. Because certain theorems won't work if you have a not closed, not simple, or closed, not simple. Some theorems won't work if you have it not closed. Yeah.
So is it not simple if it has a jagged edge or if it crosses over?
If it crosses. Yeah. Okay. And I'm really not going to worry too much about the connected and simply connected. I just want to get to the meat of this thing. So for the most part, these problems are going to say things like, given a connected, closed, simple curve, all right, well then that tells me I can do these things, right? What can you do if it's not that? Well, you haven't learned that yet, and you're not going to learn it now. So, but here's the meat of this, and this is where it gets kind of nifty. So a vector field F is said to be conservative and have you ever seen this symbol here? I'm going to show you the symbol. If there exists phi such that, and actually such that is a little, it's been so long now I forgot. Such that? Oh, screw it. Such that F equals del phi. So then what kind of vector field would F be? What is that operator? What's that operator there?
It's a gradient.
Gradient. So what kind of field is this?
Gradient.
Gradient field. I love it. And this is the potential function, right? If this is true, then if you think about it, shouldn't the integral of this be simple? I mean, what's the integral of dy?
Just one.
Why? Because of the integral of the derivative of y. So if I do have a vector field who is a derivative of some other function, it should be easy to integrate as long as it can find that other function. That would be the answer for the integral then, wouldn't it? Okay. Maybe make it. So here's the idea. And this is the math that's kind of nifty. This is the math that you could do at an earlier level if I just didn't tell you what it really was. Let's see. Blah, 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 blah. Oh, so the test really comes from the fact that, so the test for a conservative comes from the fact that if F is del phi, then F equals phi x. Let me just kind of do this. Is this cool? Because what's the gradient do to something? Does all the partial derivatives, right? So the F is FGH. Del phi, what would del phi be?
It's F prime, G prime.
Careful now. Not really.
FXG.
Phi is in FGH.
FX of GY.
Phi is not FGH. Phi is phi. When you do the gradient of something,
It's F phi, G phi, H phi.
it's phi x, phi y, phi z. Cool. So the gradient of some function is just the partial of that function with respect to x, comma, so forth. So that's why, if this is true, then f must be this, g must be this, and h must be this. So here's the cool thing. Let's see if you guys agree with me this is cool. If I take another derivative, if I do fy, that's phi xy, right? What's gx? Gx would be phi yx, which is the same thing as phi xy for most functions, for the functions we're going to see in here, right? Which is fy. And so forth. You can keep doing that. So the test actually comes from seeing if this is true. If this, then these things. And actually it's an if and only if statement. This, if and only if these are true. And do you see how you can keep going? Can you do the second one with respect to z here, and then the second with respect to y there, and get an equivalency there? So the test really is just take the f they give you, and double check if, let me see if I can keep myself straight. Fy has to equal gx. Fz has to equal hx. And gz has to equal hy. If that's true, then it is a conservative vector field. Then the whole question would become, how do you find what that phi is? Okay, maybe. So this is built on something we know already. We know that this equals that for most functions. Just for discontinuous functions at certain points it doesn't work. But for most of the functions we're going to look at, this is true. Which means then that this must equal that in order for this to be true. So how do I check if a vector field they give me is coming from some phi? I just check these things. If they are true, then I can go forward. So some of you guys, like I was saying earlier, if you've taken diffie q before, that is pretty much how you check to make sure something is an exact equation. Right? So if you have to take diffie q, then you're getting a little preview. Thankfully, in 2 dimensions, which is really, I think, what I try to focus on your homework. In 2 dimensions, these really just boil down to fy equals gx. So let's try one out. And actually, I'm going to go a little further with it than they do here. Yeah, good. So is this conservative? So whereas this piece of it is also known as little f, and this piece is little g. So all you got to do, since it's only 2-dimensional, you just have to check to make sure that fy is the same thing as gx. Right?
2-dimensional?
Well, it's oh shit! Did I give you one with 3? Yeah, I did, didn't I? Oh, well, you do that too. So now I want to check. Ooh, is there another common thing? Oh, there is. I didn't mean to do one, but well, we could do it. 2xy, 2z. 2y minus 2x. So this is f, this is g, this is h. So to do this check, we've got these things down there. If I do give you a problem like this, I'll obviously give you the little check. And it really is just straightforward derivatives, right? So to double check if this is conservative, what we do then is